Thank you, Ren. And as the others have said, thank you all for coming along, especially on Zoom. It's great to have this level of support. So yeah, I'm Luke, and I've been looking at using StructurefromMotion photogrammetry to measure the volume of our slash poles in our forests. So starting off with kind of the problem, we've had some incidents in our forests, and they've been really thrust into the public eye as well, especially with the Tolaga Bay incidents, which we can see in the imagery here. So we know we've got an issue with our harvest residues that we're leaving in our forests. And to be able to manage something, you need to be able to measure it, especially measure it in some repeatable way. So we need a method to repeatedly measure the volume of our slash poles so that we can better manage them. Currently, we're using the geometric method, which involves approximating our piles using some geometric solid, which is a nice smooth shape that we can easily calculate the volume of using some basic length, width, height measurements. But then if we get a slash pole like this, which is best approximated by the upper ellipsoid here, it is only a best approximation. That shape does not entirely mirror the shape of that pile. So we're missing some volume and we're not getting an accurate representation. So my proposal is that we can use this technology called StructurefromMotion photogrammetry to measure these poles instead. So photogrammetry is the science of taking measurements from photographs. It's been around since the World Wars, where it was used to identify enemy positions. StructurefromMotion has been developed as a branch of photogrammetry with recent advances in computing power. So what it will do is it can take a set of images that you input to the software, and it will identify common points between all of these images. So as in this example, it's identified the top of the tree in those two images and the branch on the left here in those two. It'll go through using all of the images that you put in, and in my case, identify in the vicinity of 40,000 common points between all those images, and then from that build a 3D point cloud, which is similar to what you'll get if you fly a LiDAR survey. There's similar output to LiDAR. However, this is best employed on a smaller scale. So kind of on the scale that I'm looking at, a slash pole on land. If you want to point cloud of your whole forest, that's when you'll fly LiDAR because it's more cost effective. So we are already using this StructurefromMotion technology in forestry. So in Pine up in Rotorua are using it for inventory and post-harvest analysis purposes. And there's been research done just this year out of the University of Auckland where they were using it to model accumulations of large woody debris in these kind of slash flow events. But they were only doing it on a small scale in a lab. And that's what that bottom image there is. It's also frequently used by our colleagues over in civil engineering and also in mining, where they use it for volume measurement of stockpiles of gravel and so on. It's easy for them to use it for that because a gravel pile is nice, solid, and it's very easy to fly a photogrammetry survey over and compare between to get your volumes. So the method I employed, I've kind of approached it from the simplest method that you can come into this from. So if you improve on this method, your results are going to be equal to, if not better, than the ones I've achieved here. So I photographed the pile with just a consumer-grade drone, UAV. I flew around the pile, taking photos at a 45-degree oblique angle, and then also directly over the pile. So that ensures that we get really good coverage of all aspects from all angles. Then I used a software package called AgiSoft Betashape, which has been used in a number of previous studies done in the photogrammetry area, and it's also the software package that the university has a license to. So that software will do that alignment of all those common points, identifying all the common points, and then from those that can interpolate between them and build what's called a dense cloud, which is what's visible in this photo here. And as you can see, we've got some very nice reproduction of what's in the slash pile there. And then from that dense cloud, you can generate a digital elevation model from what you can take the volume. As part of this, I was checking that the dimensions of the pile, as they are in real life, are preserved when you generate the model. So to do that, I took length, width, and height measurements of the pile. primarily so I can apply Hardy's geometric method, and also so I can check these measurements are preserved. And very happy to announce that all but one of the length and width measurements were preserved to within 10 centimetres. The other one was preserved to 50 centimetres, so that was because of the measurement issue. Height measurements were harder to preserve because we can't go up, climb on top of the pile to measure the height, so they were an estimation of the average height of the pile, and they were out by about half a metre on average, just because I'm not that great at estimating heights. So measuring the volume, all of these software packages that you can use for photogrammetry have a volume measurement tool in them, where you just draw a polygon around your pile and it will interpolate a best fit plane across that polygon, so linking all these points to create a nearly flat surface. And then using the digital elevation model, it knows the height, so it can work out the difference between your plane and the surface, giving you a volume. The digital elevation models I was able to generate during this work were of very good resolution. The one here is a resolution of 1.55 centimetres per pixel, and the coarsest resolution I got was about 4 centimetres per pixel. So even the coarse ones are still very, very fine. Depending on the number of images that you use, processing time can vary between 7 and 259 minutes. And the quality of the model and subsequent DEM are also changed with that. So low number of images, low processing time, low quality model, vice versa for the high quality. So in terms of some results, I compared mine to work done previously that compared LiDAR measurements of volume with the geometric method, which is the blue dots, and my work, which compared the StructurefromMotion volume to the geometric method, which is the green dots. As you see, they do follow generally the same trend. The geometric method that Hardy did, Long did, sorry, tended to underestimate the volume, whereas mine was overestimating at the lower volumes. That's mostly attributable to my issues of determining the height of those slash piles. At high volumes, it tends to be reasonably close, but there's still some variation, again, that's likely due to the geometric method, not the StructurefromMotion, as the measurements were preserved very well and the DEMs were of fine quality. So from that, the volume of the pile should still be accurate. These black lines are included at plus or minus 15% from the true volume. That threshold was identified through conversation with industry. Said a volume that's within 15% of the true is useful to us. So you can see that they do fall outside, but again, I've attributed that to the geometric, not the StructurefromMotion. Processing time increases exponentially with the number of images that you use. As I said earlier, from 7 up to 260 minutes. You can use a low number of images, as I say, and get that kind of lower quality DEM, which is still 4 centimetres per pixel. But when you start getting down to that lower number of images, your models can start to have some issues when they generate. For instance, there was one that I generated with 37, and half of the terrain generated at that level, and the other half generated there, just because it wasn't able to identify enough common points between all the images to successfully stitch the model properly. So the applicability of this technology, it can be used to determine the volume of slash files. However, because of that processing time, which can range for a reasonable model in a reasonable time, kind of 30 to 90 minutes, it's likely most useful for files where you've got tricky access, so you can't either get to them or you can't get safe access all the way around them to apply the geometric method. If they've got an unusual shape where they're not well represented by one of those geometric solids, or if there's a high risk that the file could fail, or if it does fail, there's a high potential for damage. You could use this method and then you've got a model of what the file was if you need it. Further to that, if you do have one of those high risk files that could cause a lot of damage, you can fly your drone at regular intervals and then do 4D modeling over a period of time so that you can monitor any potential changes in the file if it starts to slump or mobilize down down the slope. You can get ahead of it. Furthermore, you can use this for kind of small scale surveys for earthworks purposes. So this is a screenshot from Riedinger. That drone was generated with StructurefromMotion. And as you see, it's of very good quality. The utes preserve very well in the middle of the landing. You can see the woody debris and pile on the slope below. There is, as I say, a number of software packages available. This would be the next one on that Fix4D Cloud, which is entirely online, and that you can get a license for $160 a month. So it's not an enormous cost, and that's the user interface on that slide. Evaluating the volume of the same file, we've got 48 cubic meters in AgiSoft and 50 cubic meters in Fix4D. So it's very similar, and I'd say more accessible. So just to finish off, 3 key points. It is possible to use this to generate reasonable models using these simple methods that I've used. But as I say, due to that processing time, it is best applied on those kind of high-risk files and sites and those tricky access where you might not be able to get safe access. And another note, it does only provide the bulk volume, so you would need to apply a correction factor to get the actual biomass in the file. And that has been, there are correction factors